This is the first on a series on linear algebra for quantum mechanics. In this video, we'll introduce the concept of a vector space. You're likely familiar with vectors as a geometric object, where we think of an arrow like this. Instead of a single number, a scalar, the vector is a quantity with both a direction and amplitude. You may have seen geometric vectors like this representing force, for example, in classical mechanics. You may have also seen a vector represented with respect to a particular coordinate system, like this one here, where a sub x, a sub y, and a sub z are numbers, vector components, that represent the vector in a 3D space. If this doesn't make sense, we'll discuss spaces further in a future video. But for now, in the rest of this video, we'll be thinking about vectors in more abstract spaces that don't necessarily represent a physical space where we have 3 spatial dimensions. They can be in other higher dimensional spaces, use different coordinate systems, and have components that are complex. In quantum mechanics, we care about vectors and vector spaces because we're going to represent the states of a quantum system using vectors in a vector space. The fact that a quantity is a vector is often denoted with a little arrow on top. In quantum mechanics, we'll usually see vectors represented as something called a ket, which looks like this. This way of writing vectors is called bra-ket or Dirac notation. We'll show the bra-ket notation more when we compute inner products, which involves the bra part of the bra-ket, which we'll do in the next video. For now, let's introduce the vector space. All a vector space is a collection of, you guessed it, vectors, as well as scalars, which are just numbers. We could have a set of scalars that are the set of real numbers, or as we'll more commonly see in quantum mechanics, we'll also allow scalars to be from the set of complex numbers. And we call a vector space where the scalars are in the set of complex numbers a complex vector space. In our vector space, we're going to have 2 operations. Vector addition, where we have a vector, we add it to another vector, and we get a third vector that is also in the vector space. We're also going to have scalar multiplication. Here that means we take a scalar, we multiply it by a vector, and we get back another vector. And those operations are going to satisfy some properties which we should now go through. First, let's remind ourselves what vector addition is. In this small example, we're going to have 2 vectors that are both 2D vectors in a Cartesian space, i.e. the xy coordinate system. We have a vector A, and we have another vector B, and we want to add those together to get a third vector C. To do so, we simply add the corresponding components, so 2 plus 5 and 3 plus 4, and that gives us a third vector. And that's all vector addition is. The properties of vector addition that hold in our vector space are as follows. First is closure. If we take 2 vectors, A and B, that are both in our vector space, and we add them together using vector addition, the result, C, will also be in our vector space. Next, the commutative property holds over vector addition in our vector space. That just means that it doesn't matter in which order we do the vector addition operation. The result is the same. Next, the associative property holds in the vector space over vector addition. That just says that where we put our brackets doesn't matter when we're adding together our vectors, as seen in this example. Next, something called the additive identity exists in the vector space. This just says that there's a special vector, which here is shown with a 0, so we'll call it the null or 0 vector, which when we add it to any vector A in our vector space, we get back just the vector A. That is the identity for vector addition. Finally, an additive inverse exists in our vector space. That is, for every vector in the space A, there's an inverse such that when we perform the addition operation, we get the identity vector. Next, we have scalar multiplication. First, like we did with vector addition, let's do a simple example using another 2D vector in Cartesian space. We'll use our same vector A. And we'll use a real scalar that is just the integer 2. And we'll multiply our scalar 2 with our vector. And what we do is simply multiply each vector component by the scalar 2, and that gives us our result. Now let's discuss the properties of scalar multiplication in our vector space. So first is similar to vector addition, we have closure. So when we take any vector A that is in our vector space and a scalar that is in our vector space, the result of any scalar multiplication will always be in the space. We also have the distributed property with respect to scalar addition. That means that if we take the scalar n and multiply it by the result of vector addition of the vector A and the vector B, we could instead compute separately n times the vector A and then add it to the result of n times the vector B. Similarly, we have the same distributive property with respect to scalar addition. Next, we have the associative property, which again just means it doesn't matter where we put our brackets. And finally, there is an identity element for scalar multiplication that when we apply scalar multiplication to our vector A using this identity, we get back our vector A. And so for scalar multiplication, that identity is 1. In this video, we introduced Dirac or bra-ket notation. We introduced the concept of a vector space, and we discussed vector addition and scalar multiplication in our vector space. In the next video, we'll continue our discussion of vector spaces and we'll introduce the inner product.